Okay, the recording has started. Habib Hocam, the stage is yours. Thank you.
Okay, thank you very much. Hello, everybody. Good afternoon. Unlike Professor Ezzat, I wrote my lecture note in advance, and you can see my handwriting, and I will go through what I have written down already. So it wasn't supposed to be a lecture, but then I decided to make it like a lecture note that a student can follow later on. So the subject is about tensor formalism in general relativity, and let's say what is its application, what is its necessity, and the subjects around this formalism. So when we say thin shell, of course, in classical mechanics also we have thin shells. Thin shell appears everywhere. Actually, shells appear everywhere. So even in our body, we have membranes in different parts of our body. So the dynamic or mechanic of these shells in classical mechanics are very well known. And some of them are very thin, which they consider a thin shell, like a swap bubble, which separates inside the bubble from outside, maybe with different pressure, and the balance comes from the surface tension of the thin shell, bubbles thin shell. And we have also shells, as I said, in our cells, which they are thicker, of course, but still we can apply some classical mechanic rules to describe them, to analyze them, to see what is their structure and how they develop and how they evolve in time. So this is not our business actually, because those surfaces are, the classical shells are surfaces in a three-dimensional Euclidean space. Although many concepts are common with what we're going to do today. But here we are in 3 + 1 dimension. Our space-time is not anymore Euclidean. We are in the simplest case in Minkowski space-time. But in general, we are going to consider to be to stay in curved space-time. So now we're going to see where this appears. I mean, thin shells in general relativity, where they appear. When you consider let's say any two space-time to be combined or to be introduced together, we will have a kind of shell between them. So that is kind of thin shell in sort of mathematical structure. So for example, when you describe star, so stars are actually living in three-dimensional space and one-dimensional time. So outside stars, suppose they are not also rotating. So we have Schwarzschild metric, and inside the star depends on what kind of fluid or matter we have. We have different space-time over there for, the solution of Einstein equation. But the thing is, for sure, they should match on the surface of a star. So that is exactly what we're going to say here, what we're going to talk about. How these two spaces, space-time, they reach together, they glow together. And mathematically speaking, what kind of conditions should be satisfied? Can we say any types of space-time inside the star and Schwarzschild outside, they can match? And we can also make a similar, let's say, example with particles. So classically, I'm talking about everything in classic. Quantum aspect of the problem is not considered here. So you consider a particle in general. So suppose we talk about electron, classical, let's say, description of electron. How about if we think electron is like a shell, like a let's say, like a bubble, exactly like a swap bubble, inside one space-time, outside another space-time, and on the shell, on the surface, they collide. Actually, they get introduced. So what kind of condition should be satisfied? Can we consider any type of a space-time inside or outside? And these are the things we're going to discuss, but more mathematically. So, and also at the end of the lecture, let's say, I will give an explicit example, and we will see the application of the theory. So let me just make it the screen, okay. So now the outline is very short. First, I give you the tensor formalism. Of course, I write all the detail, but I will go on the surface. So then if anybody studies the lecture note, they can see the detail written down. And then in the second part of the lecture, I give one explicit example, which is a spherically symmetric tensor, of course, in general relativity. And finally, I will conclude my lecture in conclusion. So let's see the configuration in general relativity. You see here a picture. We have two space-times. One is M minus and the other M plus, two manifolds, let's say. And they are joined or glued at the surface in this specific figure. This hypersurface sigma is time-like. Well, of course, it can be also a space-like or null, but since the time-likes are more interesting and they have more application, I fully concentrated on time-like shell. So we see that the two space-times, or manifold M minus M plus, with the boundary here, you can see we have boundary for M plus and M minus. They are glued on the surface sigma, which of course surface sigma or shell sigma. It has also two parts, the right part, which is sigma plus, and the left part, sigma minus. And also in this specific figure, we introduce also the normal, unit normal to the surface and mu, which is clearly from the figure, it is a space-like vector indicating our surface is time-like. Also, as it is indicated, we have different sets of coordinates for M minus and M plus. For simplicity, we both call them X, but of course they are not the same. So one is X plus, the other X minus. Once they crash on the surface, we have different set of coordinates, of course, one dimension less this time. And also this time we call them Y minus and Y plus. Now, HAB and G mu nu, they are our metric tensor. G mu nu, they describe the manifold, and HAB, they describe our surface. So this is the configuration at the moment. And we're going to see what condition these items we see in the picture, they should satisfy. In general, we are sure that it is not random. I mean, you cannot join two random space-time together. So there should be some condition satisfied. And those conditions are very well known, and we're going to discuss. Actually, before I start, as I said, it's all mathematical approach. We consider initially, or we postulate initially two, let's say, conditions, which are almost trivial. First of all, the shell is very thin, so it means that we can ignore its thickness. And in this case, we postulate n mu, which is the normal vector to the surface, and from negative to positive manifold, is a continuous object. And also we postulate the coordinates on the surface on both sides are also continuous. So which means that y minus and y plus c, they are the same. So these two, which are very much acceptable as long as we impose the shell is very thin, very much acceptable, and it doesn't make any problem. So from now on, whatever we find from mathematical approach. But before that, also let me show you the detail of the surface once more. This is the surface, or hypersurface, let's call it. And I didn't show the coordinates or the axis of coordinate on the shell, but n mu is clear here. And also I shown here a geodesic path from the negative side to positive side, because this geodesic path is going to be our the last coordinate to describe, to establish a local, let's say, system of coordinate on the surface. So 3 of them, they lie on the surface, and the 4th one is normal to the surface, and this geodesic also is normal to the surface. So that will be our the last axis. Actually, in this way, we will work on a Gaussian coordinate system, local system. And here L is the proper distance. Actually, since we use, we're going to talk about time-like hypersurface, L is the proper distance from the surface. And we set L0 to be the location of the hypersurface. Negative L is for the negative, M negative, and positive for M positive. And of course, I already said n mu is a unit vector, which is also a space-like to make our surface to be time-like. But this can be also considered for the other 2 cases. The surface can be null or space-like. In the case when the surface is null, then n mu is 0. And if the surface is space-like, n mu is -1. But those are not considered in this lecture. Okay, to continue mathematically, we use distribution theory. There is a small typo here. We start from Heaviside distribution function, theta L, and L is the one I already introduced. It is equals +1 when L equals positive, and it is 0 when L is negative. And for L0, it is not defined. So this is the Heaviside function, Heaviside distributed function, actually. And that is not difficult to see that theta L square is equal to theta L, and also theta L times theta minus L equals 0. Just this is 0, guys. There is a mistake here. And its derivative with respect to L gives us a Dirac distribution, which are elementary definition of delta. Okay, but as we know from distribution theory, theta L, delta L is not defined. So mainly because that theta L is not defined from the beginning. So everything comes from this theta L, delta L, which is not defined. From now on, we will try to avoid any combination such as theta L, delta L, or even delta L S square. So, or the derivative of second derivative of delta, and so on. Those which are not defined in distribution theory, we will avoid. So now we start from G mono or metric tensor inside the entire manifold. So this is very clear. We can write G mono equal to theta L, G mono plus theta minus L, G mono minus. This is completely acceptable. We don't say what is G mono exactly at L equals 0, but we know when L equal to positive or L is negative, what happens to G mono. This expression doesn't tell us whether G mono is continuous or not. So only it gives us the metric tensor inside the M minus and M plus manifold. Okay, now, as I already said, L here is the proper distance on a geodesic normal to the surface. Therefore, dx mu on that geodesic is given by n mu dl. This is very much clear. And also we can simply show that from dx mu equal n mu dl, n mu is equal to d mu l. So all because L is the proper distance. And of course, here we consider n mu to be 1 because it is the unit vector, unit normal is a space-like. Now, n mu is also tangent to the, is normal to the tangent vectors. Tangent vectors usually defined in terms of our canonical coordinate x mu and also the local coordinate ya. So a and mu also, the Latin, the Greek indices, they go from 0 to 3, and Latin, they go from 0 to 2. So one less dimension for a. So now, as I have already said in the introduction, we consider n mu, the unit normal, to be continuous, and also the tangent vectors. So these two conditions or postulate, they are valid as long as the thickness of the shell is small enough. So now, as I said, from the definition of G mu, we didn't say anything about whether G mu is continuous or not. So now what we do, we just take its derivative with respect to a coordinate like d rho. So what happens here, by taking derivative of G mu with respect to rho, we have, of course, the ordinary terms, which are the derivative of G plus and G minus multiplied by the correspondence theta. However, the derivative of theta with respect to rho gives us delta multiplied by d rho L. And we already said d rho L, because of L is the proper distance on the geodesic normal to the surface, is equal to n rho. So then after you just combine the plus and minus, because of the minus sign inside theta, we will have delta L G mu nu plus minus G mu nu minus times n rho. And now we see derivative of G mu nu brings delta distribution. But we know that in finding Riemann tensor, which we needed in order to construct Einstein equation on the total space-time, we need derivative of G mu nu in Christopher symbol, which is multiplied by G mu nu up, I mean the contravariant G mu nu. So in other words, since G mu nu in contravariant form, it contains theta, and its derivative contains delta here, their multiplication brings delta multiplied by theta. So we have to avoid, and the only way we can avoid is we just from the very beginning, we say, okay, G mu nu should be continuous. So this is the first, first application of distribution theory. And then this term, I mean, the last term should be eliminated. So by accepting or by imposing G mu nu to be continuous on the surface, we get rid of delta L, and then our derivative of G mu nu will not contain delta L anymore. So what G mu nu being continuous brings to us? Actually, G mu nu means actually the metric in each side. But when it comes on the surface, we have, because these are the 4-dimensional tensor in plus and minus m. But when we come on the surface, one dimension should be frozen. So this is how we project any tensor on the surface. So the projection of a tensor like G mono on the surface, hypersurface, is given in this form, as you can see. So HAB is the projection of G mono on the surface, and it is equal to G mono multiplied by the tangent vector in each direction. So then, if G mono is continuous, we can, because of X and Y, which we already consider them to be continuous on the surface, and let's say tangent vector and normal vector to be continuous on the surface, then G mono, continuity of G mono gives continuity of HAB. So in other words, HAB should be continuous, or it's HAB plus minus HAB minus should be 0. This bracket here, the square bracket, means the value of that quantity in positive m minus in negative m, actually m plus minus m minus. So it is given here. Therefore, HAB should be 0. HAB also is called the first fundamental form or the induced metric tensor on the hypersurface. So then we found that in order to avoid delta L, theta L in further calculation, HAB should be continuous. So here, this is called the first junction condition, and we will keep in our mind. And also I emphasize again that I consider YA and X mu, the local canonical coordinate, to be continuous together with N. Okay, after we eliminated that delta L term, derivative of G mu nu with respect to rho became, as you see here. But this expression doesn't tell us whether the derivative of G mu nu is continuous or not. Actually, we have no idea whether it is, but suppose it is not. If derivative of G mu nu is not continuous, then since G mu nu is continuous and N mu is also continuous together with the local coordinate, then the discontinuity of derivative of G mu nu shouldn't be tangent to the surface. And if it is discontinuous, it should be normal to the surface. So the discontinuity of derivative of G mu nu, if there is any, it should be normal to the hypersurface. Therefore, we say actually this square bracket exactly is its meaning is the discontinuity. So d rho G mu nu in the positive side minus d rho G mu nu in negative side. If it is not 0, it should be in the n rho direction, or the normal direction. So we write it in the form that you see here, n rho that is omega mu nu. Omega mu nu is a tensor. It can be proved that it is a tensor. It satisfies the condition. And now, if that is the case, what is omega mu nu? We can just use the elementary properties of n mu, n mu, and we get omega mu nu equal n rho d rho G mu nu discontinuity. Now here, again, I emphasize that the surface we consider is time-like. So it means n nu down, n nu up is equal to 1. So now, in this case, G mu nu, which was continuous, is given here, and the derivative also is given here. But when we write the Christopher symbol, because Christopher symbol appear in Riemann tensor, we consider Christopher symbol simply, actually it is obtained because we know how to write it, and we by purpose, we avoided the delta term. So Christopher symbol also became simply theta L gamma plus theta minus and gamma minus. Now, but we don't know whether Christopher symbol is continuous or not. Actually, we have no any reason to say it is not discontinued. So then we take its derivative to see what is happening. And then after writing the explicit form of Christopher symbol, which I didn't put here, it's just straightforward, we find out a delta L appears. It's exactly like the derivative of G mu. The reason delta L appears is because the derivative of theta gives you delta. And also the mu L also appears in all our calculation, which at the end it gives you n rho, sorry. Then what is left here inside the square bracket, it's just the discontinuity of Christopher symbol. So it is given by, since we had already the expression for the discontinuity of derivative of G mu nu, and you just substitute, you find discontinuity of Christopher symbol in terms of omega, and of course the normal vector. So the detailed student, they can just do as exercise. So now we also obtain the discontinuity of Christopher symbol here. However, we said n mu and the tangent vectors e mu a, they are all continuous. This was our initial postulate, but their derivative also we can try the covariant derivative of n mu. Because of n mu is continuous, it becomes simply the discontinuity of gamma multiplied by the other component of n. Anyway, so these are very simple calculation everybody can do. And finally, we know the second fundamental form, or the extrinsic curvature, in terms of the normal vector to the Harper surface given here. In the next page, I give you a review of these formulas, which can be helpful. So then, since we know what is the discontinuity of covariant derivative of n, we can simply find what is the discontinuity of extrinsic curvature tensor, and also we can find the discontinuity of trace of extrinsic curvature K. So now all given in terms of the normal vector, and also that omega mu nu, which was actually the discontinuity, the component of discontinuity in the normal direction of derivative of G mu nu. So now here I give you a simple description of mathematical description of the let's say the formula we use here. Let me just emphasize our space-time, our bulk space-time is 4-dimensional space-time. G mu nu is its metric tensor, and our hypersurface sigma is 3-dimensional space-time, and its metric tensor is HAB. This is called induced metric tensor. Actually, here I should write DYA, DYB. Sorry, there is also another mistake here. Of course, X and Y, they have relation, that is for sure. And in terms of G mu nu, H mu nu, and the tangent vectors, we can connect them. On the other hand, Greek indices, they go from 0 to 3, Latin, they go from 0 to 2. Here is, because it is time-like hypersurface, 0, which is time, appears in both. And also, for any vector, by the way, YA, they are local coordinates on the surface, together with NA, which is in the direction normal to the surface, and it also continues on a geodesic normal to the surface, make the very famous Gaussian coordinate system, local coordinate system. And any vector VA in the space, its projection, or let's say its effect, so to say, or its shadow on the surface, hypersurface, is given in this form. Actually, this is very much like elementary vector analysis. And we also have here in this relation, if you have the covariant derivative of vector in the four-dimensional space-time, multiply by the projection, the tangent vector, you can get this projection, which means the covariant form of the derivative of the projection of same vector on the surface. So these are very basic, let's say, formulas. There are more. The surface, hypersurface, generally in a higher dimension, let's say in four-dimensional space-time, is defined any relation between x mu or let's say x alpha. And now, of course, when like phi here, when you have it, you can just simply introduce the normal vector like what we used to do on classical mechanic. This is just the gradient of phi, divide by its magnitude, which makes it unit vector. And this is the magnitude actually. And here in this case, n mu, since it is equal 1. So phi equals 0, of course, is the location of the surface. And it means that everywhere on the surface, phi should be 0. Therefore, phi is, although x mu, we have the relation with y a, but phi is not a function of y, because when you walk on the surface, your phi doesn't change. In other words, d phi dy a should be 0. Using chain rule, it gives you d phi dx mu dy a should be 0. This is the tangent vector on the surface, and this is just n mu, as we said before. So it tells you that n mu is normal to the surface or the tangent of the surface. So these are, as I said, basic formulas. HAB, or the induced metric, or the first fundamental form, can be found by using the H mu nu. What is H mu nu? H mu nu actually is a four-dimensional tensor. However, HAB is three-dimensional tensor. But H mu nu is just G mu nu minus N mu N nu. So still it is four-dimensional, I mean a tensor in four dimension. But by multiplying by the tangent vector, you get its projection, which is a three-dimensional tensor. Okay, so these are all about the surface and the space, surface and the space-time. In the same way, K mu nu, the second fundamental form, is defined as you see here. This H mu nu, it is the mixed form of the tensor H mu nu. So then it is not delta mu nu, because some students, they think it should be delta mu nu, because it's our induced metric, but it is not induced metric actually. This is the four-dimensional induced metric, which it is not actually the first fundamental form of the surface. After you find this projection, it becomes. Therefore, this is not delta mu nu. So anyway, this is the extrinsic curvature or second fundamental form. These are given in any books. You can just check. And its trace is given by K mu mu, or covariant derivative of n mu with respect to mu. And what we have used already, these are actually still four-dimensional tensor, but by just multiplying by the tangent vector, you get the projection, which are actually the second fundamental form on the surface. So we just go on with this new information. We understand what we have done before. So the extrinsic curvature, you see here, this is K mu nu. Therefore, it is not exactly the three-dimensional tensor. So it's still in four dimensions. So we have to consider as extrinsic curvature in the bulk. And this is this, let's say, trace, all we found before. But now we're going to find exactly what is KAB, which, as I said, you can just find its projection from K mu nu simply. And then since K mu nu, we just write it down, and we know that tangent vectors are normal to normal, unit normal. There is a very big simplification, significant simplification, and we will be left only with this part. You see, that is exactly the difference between KAB and K mu nu. Although K mu nu is very long, because it is in the space, I mean space-time, 4-dimensional space-time. But when we come to the surface, its projection is very short. And same for K, I mean its trace. So now these facts can be used to find, we just keep them there. And also we, if you remember, we found the discontinuity of Christopher symbol. We can use it in the definition of Riemann tensor in the space-time, the bulk space-time. Definitely after you just manipulate the terms, you get a term like what you see here. Of course, the first and the second terms are clear, they should be there, but the third term is the discontinuity of Riemann tensor. So it shows that Riemann tensor is not continuous. And what is this discontinuity? It's just given here. So the detail, as I leave it as an exercise for the student. And also when you contract R mu nu, Riemann tensor, you get Ricci tensor. Again, it will give you a part which shows its discontinuity. And that part actually is given in the last question. And you can see that after you just write it down carefully, it will be exactly equal to the extrinsic curvature with the minus sign minus the trace multiplied by n sigma n nu. So the detail, as I said, one can find easily. However, these are still in the space. So both K sigma nu and the second term, they are in the space, 4-dimensional space, in the bulk, not on the surface. So we have to find the projection. Okay, now we have here R, the last quantity to be calculated, because our aim is to use the thing we find to construct Einstein equation, or Einstein tensor. So Ricci tensor also, Ricci scalar also is the contraction of Ricci tensor, and then it's just easily given in the form you see here. The discontinuity in Ricci tensor, Ricci scalar is given also here. It's just minus 2 multiplied by the trace of extrinsic curvature. Okay, now after we found R and R mu nu, using the distribution theory, we can also say, okay, G mu nu, which is the Einstein tensor, R mu nu minus 1 over 2 G mu nu multiplied by R is also in the form that you see here. The first two terms are very obvious, but the last one, you just put the terms down, you find it. It will be R mu nu, discontinuity of R mu nu and R multiplied by G mu nu. So then after you just substitute from previous term, you find K mu nu minus H mu nu K. These are still in our bulk space-time. So Einstein equation now can be constructed because we have everything. If our action is given, as you see here, Ricci tensor, this is the action is completely in entire space-time, I mean the composite space-time. And we have matter on inside the manifolds, I mean the composite manifold, and also on the surface. You see, this time I consider also matter on the surface. I mean the surface between the two m plus and m minus. In this way, we see that G mu nu is equal to K multiplied by T mu nu. The variation gives us the Einstein equation. G mu nu we already found. T mu nu is given here, but we have two matter. One is inside the bulk, one is on the surface. So in that case, we say T mu nu has two parts. One part, I mean three parts actually. One inside the m plus, one inside m minus, and also we have S mu nu on the surface between two incomplete bulks. So in that case, if you just put G mu nu forward and equate it with T mu nu in the form we said, we get equation which is called second junction condition, K mu nu minus K times H mu nu equal minus K S mu nu. So all you see in this equation are in the bulk space-time. We have to make them localized. So by just finding their projection. So we know how to find the projection by just multiplying by tangent vectors. And this is not also difficult. Let me check the time that I have. Okay. I think I am going to be running out of time. I have 15 minutes more. Can you just inform me? Okay, so I just go on. After we find the projection of K mu nu and of course H mu nu on the hypersurface, we find finally the second junction condition KAB minus KHAB equal minus KSAB. Now here we see that both second fundamental form and its trace, they are not supposed to be continuous. And we also already observed even R is not supposed to be continuous. So, and R mu nu also is not supposed to be continuous, and Riemann tensor also. But the only continuous quantity, I mean, the only continuous quantities, let's say, one is the bulk metric tensor, and also the first fundamental form of the surface, and also N mu and the tangent vectors. So now, just as a reminder, what we found as first and second junction condition can be also found directly from the variation of the full action, which I'm not going to consider here, but just for your information. And SAB from the variation is given by minus 2 dl matter on the surface DHAB, so plus HAB plus multiplied by L. So what I say, if you find SAB directly from variation, it should satisfy energy momentum conservation equation or condition, which means covariant derivative of SAB with respect to A should be 0. This is very important equation or law, let's say, and it tells us the energy momentum on the surface is conserved. So now I am in the second part of the... yes.
You have half an hour left still, so...
Okay, very good. Thank you very much.
Time.
Because I need all my
Sorry
time.
about later.
Okay.
Thank you.
So now let me just tell you what happened. We used distribution theory. The only matter was we were avoiding any undefined combination between theta L and delta L. And then we just applied Einstein equation. Of course, previously we found all the materials in terms of what I said. And then we came across two conditions. One is called the first junction condition, which means the first fundamental form of the thin shell should be continuous. And then the second is, say, the second fundamental form or fundamental, form or extrinsic curvature is not going to be continuous. And it satisfies certain conditions, certain equation. It's like Einstein equation. Actually, this equation is very much like Einstein equation, as you see. Although if we consider K to be R over 2, in many cases, especially when we come to a two-dimensional surface, K is equal to R over 2. So then it is kind of Einstein equation with a minus sign different. And that minus sign is because of our choice of direction of N mu. Anyway, when we come to the example like what I'm going to give you, you will see the actual application of the theory. So now I'm going to establish a bubble in the space-time, in four-dimensional space-time. So it means that we have, as you can see, a spherical shell. It's really time-like shell. It's just R equal, I mean, the small r equal capital R is just a shell. It's a sphere, like a swap bubble. Inside, I'm going to consider the space-time to be flat, but outside, we're going to consider it to be Schwarzschild. So as you know, Schwarzschild space-time is outside any spherically symmetric object, which is not rotating, of course, and static. So it can be a black hole, it can be a star, it can be even the one you see on the screen now. So when you see Schwarzschild space-time outside some object, you can know what is inside actually. So is it empty like what you see here? The mass of the Schwarzschild metric outside may be all because of the matter distributed on the shell. So the good thing about this theory or this model is in Schwarzschild space-time, if it is a black hole, we have singularity problem. So we have a singularity at the origin or at the center of the object. But now in this way, we can cut that singularity out. So if I consider inside this, this sphere to be flat, it means we have no singularity left. But still we have Schwarzschild space-time outside. Now only thing we have to keep in our mind, R here is the radius of our shell. It should be bigger than the radius of the Schwarzschild radius. We don't want to have any horizon outside. Anyway, so inside, as you see, we have flat Minkowski space, as it's written ds minus, and I consider m minus inside, m plus outside. And outside is ds plus, and it's given all here, so I don't give the detail. So n mu is from inside out toward outside, and the induced metric can be found easily, directly, I mean. You just consider R to be equal to capital R, and for outside, I write it like that, but since if R is constant, so it should be 0. So then, and that is for the case if we have a static shell. So this second term will be 0, and then we will have what is left. But now we're going to consider a dynamic shell. So it means that the shell will be time dependent, but which time? The best is because the time inside and outside, they don't agree with each other. So we know that inside and outside, they have different coordinate system. Therefore, since they don't agree, we better to consider a time that both they can measure at the same time simultaneously. So that is the proper time on the shell. So then we consider R here to be proper time dependent. So in this case, dr will be r dot multiplied by d tau. So this is what happened here. And now since this is d tau, we expect, I mean the proper time, we expect the expression to show it. So what I mean, we can just take d tau out and then by taking d tau out, it's written here actually, you will have some term left inside. And then I make it 1 because if it is proper time, its coefficient should be 1, we know that. Therefore, t or t plus in this case, t dot means dt d tau, also will be connected to r dot. So similar we can do also for the negative side, and then if this is 1 and this is 1, both of them will agree. So ds plus ds minus will be the same. At least they look the same. This is minus, by the way. And then in order to satisfy the first junction condition, already tau became the same. And then theta plus and theta minus should be the same together with phi plus and phi minus. So now we have ds plus square and ds minus square. They are the same, provided these two conditions satisfied, and also theta plus and theta minus to be theta, and the same, and also phi. So now we have everything, provided these two relations are accepted. So these are very important relations by now. So what are these? Actually, they show how the time of the outside observer change with the proper time. And this shows how the time of inside observer change with proper time. So that is it. And these dot all are with respect to tau. So we agree that the two observer inside outside they don't measure the same time because their space are different. One is flat, the other is curved. So therefore, no reason to say their times are the same. But if both of them they have flat space, then actually they would be the same. Okay, now we have to apply the second junction condition, but we need Kij. Kij, although we have, I gave you a few formula before, but the practical one is here, one you see here. So actually this is found from the opening of those equations. So Kij plus or minus is equal to minus n gamma plus minus. And now this is the second derivative of the canonical coordinate with respect to local coordinate or Gaussian coordinate plus the Christopher symbol according, corresponding Christopher symbol times the first derivative. So now, actually, as I said, these are coming from the covariant derivative of n. After we find n, which is also, this f here works the rule of phi in our previous chapter. Anyway, since the time is short, I just go a little bit quicker. I found n gamma. All details are written here for plus and minus. They are the same actually. But although they are the same, when you find them in terms of their own coordinate, they don't look the same. And after you just consider those t plus and t minus dot to be in terms of r dot, then they will look like the same. So anyway, this is what I have done. N gamma plus minus, after all, they became as you see here. So then I used the time-like condition, actually a space-like condition of n mu, and then I found what is delta. These are all given the details here. So finally, n gamma plus minus became all the same. You can see here, except t dot plus minus are, of course, not the same. The expression are the same. T dot plus and T dot minus both are given here, but psi plus minus for inside psi is 1 and outside is the Schwarzschild metric. So after we have n gamma, we can find Kij, which means the extrinsic curvature on the surface. And these also are given all the detail with detail all here. You can see we found K total all given here, and also K theta theta and K phi phi with the formula that we had. And also I used the expression that we have for T dot square to find finally what are these extrinsic curvature components. And I wrote them all together here. So now, of course, I made it in a mixed form because it is easier to be worked out. I mean, more economic in terms of writing. And psi plus and psi minus also are given in this form. So now what happened? After we have Kij explicitly for inside and outside, we can find their, let's say, trace and write down the Einstein equation on the shell. So this is what I'm going to do. But as you see here, for inside and outside, because of the different structure of space-time, Kij and trace of Kij are not the same. So therefore, when we take they're different, they are not zero. Of course, they are not zero. They are. Each of them is discontinuous. So writing explicitly the total component and theta theta phi phi, we get the equation. But how about Sij? Sij also is a matter field. The energy momentum tensor a matter field on the surface, hypersurface, on the shell actually. And we consider to be just a perfect fluid with minus sigma pp. Minus sigma or sigma here is the surface energy density. P here is we call it angular, let's say, pressure, or it is just a minus sign multiplied by surface tension. Okay, after you just put it inside the second junction condition or the Einstein equation on the surface, we get what is sigma and what is P. I found them all here. Sigma is given here, and P is here. You can see that they are dynamic because R dot appears everywhere and R double dot. So now if we consider it wasn't dynamic, which means R dot to be 0 and R double dot, then we would get their static value. This is what I have done here. So these are the static value. And very interestingly, if you look, if you just take R to be very large, sigma becomes GM, actually we become M divided by 4 pi R squared. So this is very much like the classical definition of mass density on a surface. So very interesting. Of course, this is when R is very large. And this is because M is the ADM mass of the Schwarzschild metric. Okay, coming to the case, what we have started, we had a shell inside flat, outside Schwarzschild, R0 bigger than Schwarzschild radius, and we found the energy momentum tensor on the shell, which can support the shell to be in equilibrium with inside outside. Of course, sigma 0, P0, and the other parameter like R, they have connections. So the connections all are given here. But now what I'm going to do, I already said here, all the energy conditions are satisfied. Now I'm going to check whether it's stable or not. Such combination of such object, constructed object in the space, can it be stable in general? So in order to find this stability, we have to check whether if you perturb it, whether it will stay oscillating about its equilibrium, or it will just decay, or it will collapse. So this is how we do it. And it's like exactly swap bubble. So when you have a swap bubble, when you perturb it, mostly it explodes. So then it just blew up. It means it is not stable. But there are cases which they may start to oscillate about an equilibrium radius. That is the indication of stability. This is exactly what we're going to do. We're going to perturb our shell in radial direction to see whether it will start to oscillate, or it will either blow up or it will collapse. So in one case, we say it's stable, the other we say it is not stable or it's unstable. Okay, now how we can do that? That is exactly what I'm going to do in the rest of 15 minutes of my time. If you remember, I already said Sij should satisfy conservation of energy conditions. So Sij, its covariant derivative should be, with respect to J, should be 0. So this tells you, I mean, practically tells us the energy doesn't go off from the surface. So in that case, let's write it directly, I mean, explicitly what it is. So if you just open it based on our Sij, I did all the detail here. I'm not going to spend time on that. We get at the end this equation. So d sigma d tau is equal to minus 2r dot over r sigma plus p. This equation is just the explicit form of our energy conservation equation for I equal tau. So then if you just divide it by r dot in both sides, you will get an equation which is very helpful. That equation is, I think I wrote here, okay, it becomes d sigma dr equal to minus 2 over r p plus sigma equals 0. This is what I say. Now, what we do, it's written here actually, you can see. What we do, we consider the shell is in equilibrium at r equal r0. And at that moment, r dot is 0, r double dot also is 0. Then we perturb it. So it means that we give initial velocity, radially initial velocity to the shell. So then we will just watch what happens. So in that case, but before that, we remember this condition should be satisfied all the way. Actually here, what is C, I wrote here, for any perfect fluid or any fluid in general, we always have a kind of energy of a state. So it means a relation between P and sigma. So this relation is very important because different type of fluid, they have different equation of a state equation. So now here I consider P to be a general function of sigma and also R. So in thermodynamic gases, P is just a function of sigma, but not R. R is position here. So we consider P not to be only a function of sigma, but also function of position. We call it variable equation of a state. That is quite understandable because our shell is expanding, let's say, and then the structure of the, let's say, fluid over there after the expansion may change. So then the equation of a state may also vary in terms of R. Anyway, if we do that, we have sigma or Kc, a function of sigma and rho, and this condition which came from energy condition should be also satisfied. Now, what I do, I have sigma, which I found already, and from this sigma I can find R dot. So if I find R dot, I have R dot square plus VR to be 0. So from this equation, from the expression that we found for sigma. So this equation is just an equation for the radius of the shell. So it's a one-dimensional equation. So then we know what is exactly the potential our R, undergoes. And VR is given here in terms of our space-time. So now what I will do, I will expand VR in terms of its equilibrium radius, and I keep up to the first order. And then actually the first non-zero order, I say. And then we will see whether the motion with a small perturbation will be oscillatory or exponential. So very simple. This is what I have done here. So we open VR or expand it in terms of, about R0, which is the equilibrium. And this is what you see. And now to do so, we see in the expression of VR, we have sigma. And sigma, when we take the first and second derivative, we need sigma prime and sigma double prime. But fortunately, sigma prime are already found for you here. And we can find also sigma double prime. So in this case, we will get rid of this obstacle. And then directly I write the answer. Sigma double prime is here in terms of Kc and its first derivative. And sigma prime also was given before. Then we find V0 prime and V0 double prime at the equilibrium. So very trivially, V0 becomes zero because we said it is equilibrium. Its first derivative also is 0, which again means it is equilibrium. But the second derivative is not 0. So it comes after very long manipulation. It comes in the nice form that you see here. But psi 0 here is nothing but 1 minus 2gm over R0. Now we have alpha and Cs square here. What is Cs square? Cs square is derivative of P with respect to sigma. This is the speed of sound actually. So in thermodynamic, when we talk about a perfect fluid, the derivative of P with respect to sigma gives you the speed of sound, and the speed of sound should be less than 1. So 1 is the speed of light. Therefore, Cs square here should be less than 1. However, alpha is the derivative of P with respect to R, and we don't know, it can be anything. Now, finally, after you just put it down, you get this equation because V0 and V0 prime 0. And now everything depends on this V0 double prime. If it is positive, we will have a kind of oscillatory motion. If it is negative, we will have exponential motion. So exponential means when you perturb a little bit, it goes to the end. So if you perturb it toward the center, it will collapse. If you perturb it toward outside, it will just explode. So this is exactly what we're going to do. We have an indicator now, V double prime at equilibrium. So V double prime, I already found it. And now how I just examine it, very simple. V double prime is a function of, let's say, R, alpha, C squared, etc. So what I do, I make it 0 to find where it is 0. Then we find which side it is positive and which side is negative. So we make V0 double prime equals 0 and solve it for C squared. So this is what I have done here. C squared is here. And then we will see, we will plot C squared and find which part it is positive and which part it is negative, actually V double prime. And then we find the stable region. So now here I introduced X to be kind of, sorry. Yes, X to be R0 divided by R0 RS, which means short-sheet radius, and alpha also in terms of beta. Anyway, these are just the technical part. And now we have C squared in terms of X. X indicates how much is the radius of your shell. So now I plot C squared because it's nonlinear. I cannot find exactly where it is 0. So I plot C squared, and then what happens? Let me just show you. I have to change. I couldn't combine two files that I have here. Sorry, I have to share another file now with you. Okay. Do you see again my new screen?
Yes. Yes, we can.
Okay, very good. So I am sorry. I have to use another file because I couldn't combine them. This is just a picture produced from Maple. Anyway, this is C squared in terms of X, as you see. And the blue and the curve are for different value for beta. As you can see here, the green one is beta 0, which means our P is not R dependent. What we see, the upper part of green curve is the stable region. So it tells you that if you make a shell with radius, let's say 2 times the radius of short sheet radius, it is stable if the speed of sound is bigger than certain value. That value is almost 0.2. So it means the specific, we need a specific material where how the speed of sound is almost 0.2 times the speed of light and higher in order to have the shell stable. So that is almost, you know, impossible, let's say. Then when you consider your equation of a state variable with R, you see the blue one. The blue here is beta equal minus 0.1. So the derivative of P with respect to R is negative. You see here, it gives the possibility that we have a stable thin shell for any value of speed of sound, but the radius of our shell should be bigger than this, let's say, radius, which is something 1.5 of short sheet radius. So that is great. So now we understand how the system works. So the different material may give the possibility of having such kind of a spherical shell to be stable in the space, four-dimensional space-time. So this was an example. And now, as I said, it is over. I'm going to show you some of the references I used. These are maybe old papers, but the concepts are given very well over there. You can, this is very old by Israel, and these conditions also are called Israel junction conditions. And another one from Israel. So this is from Sinovila, also is very informative. And finally, I'm going to give you some conclusion. So we learned junction condition in general relativity. So it's a standard general relativity. So the question is, if you go to other theories of gravity, like FR gravity, or I don't know, Gauss-Bonnet theory, or higher dimension low log theory, what happens to the junction condition? They are very much studied already. And any new theory comes, I mean, any modified theory of gravity, they have their own junction conditions. And based on those conditions, we may have different shells surviving there, stable there. And application of the theory is in making thin shell wormholes. Plenty of papers you can find on internet. Gravistar, also other types of, let's say, black hole without singularity, regular black holes, and other, let's say, applications are given here. You can find more on internet. So thank you very much. This was my lecture today. I think I finished on time.
Thank you so much, Habib Hocam. Yeah, you finished exactly on time.
Okay, I'm happy.
Yeah, before we stop the recording, we can actually take a few questions if there are any. Are there any questions from the audience?
I think audience became bored from the mathematical aspect of the. Yes.
Well, this is a rather advanced topic, so I guess we need some time to digest and to form questions. Like, it's not immediately easy to come up with a question in such a hard topic. Yeah, I also need to like think a little bit more and digest the content. But it was helpful. Thank you so much. Okay, now I'm gonna stop the recording. Just a second.